So welcome to the last session of day one of the Vision Summit. It was pretty cool so far, I think. And now it's pretty much just me that is standing between you and food and drinks there, right? So I hope I can make the next 30 minutes worthwhile and you won't regret staying with me here. All right, so we will talk about massive mixed reality, how you can leverage existing assets and render them for mobile XR. So mobile VR like Gear VR, Daydream. Also mobile AR like smartphones, and of course also mobile mixed reality, and I have the HoloLens here with me, and I will also show you some demos with that. And I'm talking about the HoloLens as well because we've been part of the HoloLens agency program since 2015, so we got access to the hardware and the SDK back then, and since then we talked with a bunch of clients in the professional services and enterprise. And what they typically have is they have, of course, existing assets, right? They have existing CAD models, existing 3D models. And when we talk with those clients, they usually come to us and say, okay, look, we already have assets. We already have 3D CAD models. We want to use those. We don't need your 3D artists doing anything, right? We have all of those. And does it work that way? Not really, right? So who of you has experienced that as well? So pretty much everyone. So cool. So let's talk about some of the strategies. And in the next 40 minutes, I can really just give an overview, but I hope it will give you some pointers where to look for as a next step. And when I'm saying those models, CAD models, or you cannot just render them on a mobile platform, it's mainly because they're just too big. They have too many polygons. They have too many also materials, textures. There are a bunch of things that don't work because they are actually made for offline rendering on a desktop platform, right? And we are targeting real-time rendering, and we're targeting then on a mobile platform even then, right? So it's even more complex. And for the HoloLens, for example, we want to have something like 100,000 polygons. Sometimes you can get a bit higher, sometimes a bit lower, depends on your scene, on the actual model. So a couple of words about myself. My name is Rene. I'm Director of Global Innovation at Valorem. I also run the Immersive Experiences team. And I'm also a Microsoft MVP for Windows development, which is an award Microsoft gives to independent experts. So I'm not paid by Microsoft for anything I do here. I just like to share the knowledge and talk at conferences, blog about it, and also have some open source projects. One of them is an AR Toolkit port, so you can probably sense from that I'm doing this since a couple of years now. Okay, quick video about the company. We do not just immersive technology, but actually like broader stuff, also Azure, Office 365, and so on. But this video is showing you some of the work we have been doing for the HoloLens. Enough of the marketing, huh? So mobile is a challenge, of course. Why? Well, we have limited hardware. That's the main reason. We have limited memory. We have limited graphics memory, so we cannot load the full model into graphics memory. It's just not going to work. We also have limited shading units, so we cannot process all those millions of polygons on a mobile platform. Another thing is, of course, highly tessellated objects, highly tessellated models are not going to work well on this platform. And when I talk about highly tessellated, I mean very small triangles. This is the case because we will end up with overshading, because typical graphics processors, they have a certain minimum unit of pixels they process at once. It's 8 or 16 pixels, depending on the platform. But what it means is if you have a triangle that's smaller than, let's say, 16 pixels in the end, then you end up processing those pixels multiple times, so you're overshading those. So what you want to have is not those smaller triangles, you want to have bigger triangles so that you don't overshade. Another thing that is very expensive, especially in mobile, is of course draw calls. So if you have lots of different models with many polygons, they will actually be multiple meshes, right? And then you also maybe have different materials for those, so with different textures on top of them, which means you have lots of state changes because you need to submit those as different draw calls. And that is very expensive on a mobile platform. So how can you tackle that? Well, reduce the data. So, but well, how can you actually do it? There are multiple ways. And one of them is, of course, you can do that during the tessellation phase. So let me expand a bit on that. When we're talking about tessellation and CAD modeling, in CAD modeling, you're actually representing your models not as meshes typically. So what you represent those models in is a parametric modeling way. So for example, if you think about like a beam or handrail, which is pretty much a cylinder in the end, what you have there is in a CAD program, you have a representation of a point and then an extrusion axis and also the length and the radius of that cylinder, right? But what you will need to send to the graphics card and what you also need to use in Unity is a tessellated model. So you will need to submit triangles and vertices. So you need to transform it from the parametric representation into that polygonal, into the tessellated representation. So and if you have access to the original CAD files and you export that from your CAD program like AutoCAD, PDC Creo, Autodesk Inventor, or like there are a bunch of programs. In the BIM industry, very famous is Revit or the Tekla tools and Trimble, right? So if you have those modeling programs, those CAD modeling programs, they usually have a way to export it into a mesh, into a tessellated representation. And there you can usually define also what the level of detail of your exported model should be. So that is, of course, a way, if you have access to the models, if you own those models, or you could talk with the clients to get those in a certain tessellation level. But typically, you don't have that. What you get is an FBX or an OBJ file, so you already get tessellated objects, right? So what you can do then, you need to optimize it in post-tessellation, so after they are already tessellated. And you can do it manually or automatic. Another option is, of course, offloading the rendering. So you don't do the rendering on the actual mobile platform, but you actually do it on a server or PC, and then just stream the results to your mobile platform. And for the next couple of minutes, we're going to focus on the later pieces, because those are the most typical use cases. Well, manual model reduction, straightforward, right? You have a 3D artist that takes your 3D model and then reduces it. He can also get some help from like tooling that is built into 3ds Max or Maya. They usually have some tools available, or other programs typically also have some support there. But of course, it's very labor intensive, so you spend a lot of time actually, and it's very, of course, labor intensive also means it's very costly. But the good thing is you have high quality, and another benefit is, of course, your 3D artist is a human, so he can talk with the client, which is a subject matter expert in the field. So an example, when we worked with a client in the architectural industry, they told us, okay, we have all those nuts and bolts in the model, but we don't want to see them. We don't care about those. So the 3D artist could actually go there and remove all of them. You know, on the other side, an automatic algorithm wouldn't know about it, so it would just reduce those as well and could end up with lots of artifacts. So the benefit of manual reduction is, of course, higher quality. So what can you do if you don't have the money to actually do a manual reduction? Well, you can go with an automatic model reduction. And there are different tools available, because also manual model reduction doesn't scale very well, right? So you cannot have an army of 3D artists if you have thousands of models to optimize. What can you do? There are tools like Simplygon or Umbra and a few others in the market that can help you to support that. And they have a bunch of algorithms implemented, and we could talk like multiple hours over all those algorithms, but the most important ones is edge collapsing, vertex welding, to just name a few. And what they do basically is they check for a certain threshold, how close the edges are, and then collapse those. So we end up with bigger triangles. Another way to reduce draw calls is, of course, if you have multiple materials with lots of textures, you can actually make one bigger texture where you merge those smaller textures into one bigger texture atlas, so you don't submit that many draw calls, right? If you just have a bigger texture, remap the UVs, you just have less draw calls. So then you could also have different level of details there. And those level of details can be selected dynamically during runtime. So what you could do is you could take your 1 million polygon model, for example, and reduce a version with 100,000, one with 10,000, and maybe one with 50,000, something like that. And then depending how close the camera to the actual object is, it could pick the right level of detail, right? If you're a bit further away, you don't need to see all the details. So that is what Simplicon does it with a static level of detail. So they basically also generate you an LOD group and then select the different model. Umbra does it a bit differently. They create basically dynamic level of detail. So they split up your whole mesh in the scene into smaller pieces, and then they can dynamically select the pieces that are currently in view and need to be shown in a higher level of detail. Umbra also supports occlusion culling, so you might already know that. It's also part of Unity, the occlusion culling piece. And here in this example, you can see on the screenshot, I will also show it to you in the demo in a second. There is like a big city, you have lots of skyscrapers. So if you have those skyscrapers in front of you, you actually cannot see the stuff that's behind it. But what you will do is you will still submit those polygons to the graphics card, although you don't need to do it because you don't see them, right? And what occlusion culling does, it basically doesn't submit those polygons to the graphics card, which you cannot see. And of course, this is all done with some pre-processing, right? You do some pre-processing of the data and then have a faster runtime execution. It can also stream, so you can stream from the disk or from the network so that you don't end up having everything in memory. Okay, so let's switch to a demo here. I'm going to show you the Umbra plugin for Unity. So this is Unity 5.5 I have here. And here you can see the model, which I just showed you. It's a 30 million polygon model originally. So you can see all these little tiny details here with a bunch of trees and whatnot, very, very detailed, right? So if you have the Umbra plugin, you can have that in here, and you need to submit your cloud token, so you need a license key. And then it does the pre-processing actually in the cloud, right? And then there's a thing here called smallest feature, which basically defines how's the smallest level of detail you want to have in your application. And then you can hit this, and then you also need to find an output folder where it basically puts the pre-processed data, and it will be actually in streaming assets. So then you hit the Umbra 5 button, it does the computing in the cloud. It takes a couple of minutes, or it could even take hours, depending on the model, or also if you want to use ambient occlusion and other advanced features. But typically, it's pretty fast, actually. So once that's done, it will add an Umbra runtime component in your scene. And this runtime has a bunch of settings, most importantly, the input location, where it loads that streaming assets data, right? So let me play that here so you can see it. There you go. And you can see, when I move this piece here, you can see that it fetches in only the visible parts, right? And also watch the big wheel down there. If I move a bit further away, higher level of lower level of detail. If I move closer, higher level of detail. All right, so that's in Unity. That's in the Unity editor. Let me switch to the HoloLens streaming application so that I can also show it to you in the HoloLens, actually. So you're probably familiar with this mixed reality capture. There's always a bit of latency, so you want to avoid that. Say hi to the camera. Yeah, you got it. All right, so let me open the app. Of course, I call it Holo World Umbra. And then give it a couple of seconds. So you can see it fetches in the data. And this is, I didn't select the highest level of detail. I didn't select like the very smallest features. You still see some artifacts, if you will. But you could go much higher than that. And so I need to be careful that I don't fall off the stage here. But you can see that it fetched in the bridge after a couple of seconds. And yeah, there's more stuff back there. And well, you can get it, right? All right. So it actually works in the HoloLens. That's pretty awesome, I think. So let's go back to the presentation, because we have not much time here today, but I have so much stuff I want to show you. All right, here's also a video, just in case my demo would not have worked, right? I have a video also prepared, and it was actually with an earlier version of Umbra, but it works pretty cool, and the guys are working hard on it, so they're always making iterations and good progress there. can see that. It even works in winter, right? There's snow. That's my backyard when there was still snow. So coldness doesn't affect it. Yeah, you can see the bridge pretty nicely as it pulls in the data. And they made some good progress in the newer versions of Umbra. It's actually much faster now. All right, I think that's good enough. So how does it actually compare? And I'm talking about an original model here that we got from an architecture company which had 500,000 polygons, something like that. And the overall structure looked pretty good. And they have like lots of those beams in there, right? And if you look at those, that beam here, it's actually a cylinder. And if you see how badly it was tessellated from the CAD export, it's insane, right? It's hundreds of triangles, but pretty much wasted, because it's super round. So then I run it through Simplygon, and that's what came out of that. And you can see, of course, Simplygon doesn't know this is actually just a cylinder, so it doesn't know, the overall shape of it. So it reduces it, just like general edge collapsing, and so you will end up with some small artifacts there. So what would a 3D artist do in that case? Well, the 3D artist would talk with the client, and they would tell him, we're not so much interested in all the details of those beams, we're more interested in the overall structures of all the beams in the building, right? We don't need to see all the roundings there. So what would a 3D artist do? Well, he would make an extruded cube, 12 triangles, right? It's much better than like hundreds of triangles with the original one. All right, another example, a Z shape, a certain shape in a building. And you see it's lots of like details there in the angles. And automatic reduction with Simplygon again, it does a good job, but there are still some small artifacts. 3D artists would do it like this, sharp angle, be done. And again, I'm not saying automatic reduction is not good, but I just want to show you that this is like some of the typical use cases we had. All right, so what is the third approach I mentioned? You can actually not reduce your model and go with the full detailed model. So how can you do that? Well, you actually run the computation on a server or on a PC. So you offload the rendering. And there's one example with the HoloLens. It's called holographic remuting. And I will show you a live demo in a couple of minutes. So when you put on the HoloLens, it sends basically all the input, like the gestures and the head rotation, to the PC. It does the computing, the scene rendering on the PC, and then it has basically 2 video streams it's sending back to your HoloLens so you can see those video streams there. Benefit is, of course, you can reuse the original model and you have lots of details there. For example, here you can see the fence, all those tiny details, I can render them because I don't have to reduce the model. And I can also apply some nice effects, screen space effects like depth of field, anti-aliasing, which would be much too heavy for the HoloLens. Latency is, of course, the big thing here. If you have a good Wi-Fi router, you can actually get like 20, 30 milliseconds latency, which is not bad and works pretty good for static scenes. So if you have like lots of animations going on or lots of like moving pieces in your 3D model, then of course this is not a good option. But just for viewing it static, and if it's very close by the rendering, if you can have it in the same room, then it's actually a good option. Cool, so let me show that to you. So let's switch back to Unity. And we can disable the Umbra runtime, so we will end up actually rendering the original model. And then with Unity 5.5, there was this holographic emulation introduced. And one of the modes there is remote to device. So I can actually remote to my device. So I have the IP address of my HoloLens already entered. So let me put that on. And let me open that again. And put that on the site. So now I'm launching the holographic emulation, the holographic remuting player on the HoloLens. So this is an app you can get on the store. That's pretty much the player you want to have. And then you can connect in Unity. Okay, well, that sounds terrible. Let me do that. And then I can hit play here. Let's see how well it works. Okay, you can see it, hopefully. And what you can also see is down left there, the update is already done in the Unity editor, right? And so I have the full 30 million polygon model here in the lens. And if I walk in it or do head rotation, it's sending actually the input back to my computer, does the rendering there, and then sends it back. And like I said, that's a good option, so you can see all those details, and I could also apply all those crazy effects. All right, so let me stop that, disconnect, go back to this. So this is holographic removing. And of course, you can also apply that for VR platforms, Samsung Gear VR or similar ones. You would just have to implement it yourself. All right, so time for conclusions. We have 10 minutes left, so I want to spend some time also for, some questions, hopefully. And I know you're all hungry. The day is late. So what should you choose, right? Well, it really depends. It's like always in computing, it's the same answer, it depends. There's no, at least not now, no golden path. So what does it depend on? Of course, most importantly, quality versus budget, typical trade-off. So a human manual reduction always looks better, but it doesn't scale. It's also very cost intensive. So a machine can do a much cheaper job, but the quality might not be as good. It also, of course, depends on your model. So if you have a certain size of a model, and we researched that with multiple dozen of actually different models for architecture company, and we reduced those to 5 to 10% of the original size, and that still look good, so you won't have much artifacts. I recently also had a model with an energy plant, an outdoor energy plant, where you had all those tiny details, and occlusion culling wouldn't work very well there. So that's another piece. And of course, it also depends on the modeling quality of the original model. So if you have a purely modeled model or a purely tessellated one that is exported from a CAD program, you could end up with lots of holes after the automatic processing. Or sometimes our 3D artist tells us, like, look, guys, I can be much faster if I do it from scratch, actually. So modeling quality is, of course, important. Interactivity, I just mentioned it. If you want to offload the rendering, if you want to use something like holographic removing, then, of course, you need to think about interactions. So if you don't have a lot of interactions, if you don't have a lot of dynamics going on, well, then you can really output it and offload the rendering to a different machine. And the best part is, of course, a hybrid approach, right? Where you combine multiple things. For example, remember the model I showed you with that city? You had all those small trees and cars and all those tiny details, which actually don't matter that much if you're viewing it in an architectural collaboration in a meeting or something like that. So you could go in there, spend 5 minutes, kick everything out, like those tiny details, and then run it through an automatic tool, and you will end up with a much better result. We also researched for 2 clients how to build that in a full processing pipeline. And of course, we would use actually the original CAD models and do the tessellation on the back end there. And we worked with architecture companies, and they use tools, like I mentioned, like Revit or Trimble tools. And in this BIM world, they have a certain model format called IFC. And this IFC model format also has this typical parametric representation of your objects. So what you could do there, of course, you can build that in a pipeline, in a backend pipeline, in the cloud, and actually process that and tessellate it automatically. And then after that, if you still have too many triangles, you can run it through a thing like Simplygon or Umbra. They also have APIs, so you can do that as a next step. And then you could still check it, what is the output, maximum triangle count, and if it's still too much, you can go to a different route so that actually a human processes it. But with the automatic processing, you can probably get most of the models already reduced. The main conclusion here, there's no magic button, right? That's the main thing we need to talk about. There's really no magic button, not yet, right? So this is coming, I'm pretty sure about it. So for example, if you saw Microsoft acquired actually Simplygon beginning of the year. And so I don't know all the details that are going on behind the scenes, but I know that Simplygon and Microsoft, they have lots of smart folks. So they might be working on something pretty cool. So it's a good thing to keep an eye on. And I also know that my friends from Umbra are working on some pretty cool stuff. So also watch them, there's some good stuff coming. But I mainly mention that because we not only live in the age of immersive technology, we also live in the age of machine learning and deep neural networks. That's the main thing here. And just the other week, I think it was last week, a paper was released from University of Princeton. And those guys did pretty cool stuff. So devices like the HoloLens, they have a depth camera, right? Also the Kinect, you might probably remember, has a depth camera built in. So what those guys did is they can take one depth image, which is always sparse, right? It has missing pieces, and can fill in those missing pieces. So let me give you a better example. So if I take like a depth camera and would record this table, it could not see the stuff behind it, right? What they did is they trained a couple of neural networks, so they actually have not just one neural network, but a system with multiple neural networks, and they trained it with 45,000 different interior settings. And so you might wonder, how did they actually get all the training data? It's pretty cool. They actually crowdsourced it. So there's a service called Planner 5D or something, and they have a gallery where you can upload your interior designs. So they took that, and then they actually went in those models and manually labeled all the items. So they labeled it like, this is a table, this is a computer, this is a bed, or whatever, right? So now what they can do is they take one single depth image and can get out a full voxel representation plus the labeling on top of that. And that is pretty awesome. So now think about our model reduction problem. If you have just an army of 3D artists, or maybe a smart algorithm to produce those different model representations, you could actually train the neural network or like a system of neural networks, and you will probably end up with a very, very good result, which is close to a human or might even be better actually than a human. So this is coming in the next couple of years. I'm pretty sure that this will happen. That is the vision here, pretty much. So we don't have the magic button yet, but it will come, I'm sure about it. All right, with that, thanks for your attention. If you have any questions, step up to the mic. We have 2 minutes or 3 minutes left. And if you don't have any questions, I will also be at the reception later, so you can talk there or ask me online. Thank you.